Okay, so we're going to have Sasha Migdal back because we couldn't get enough of him the first time in this series of evening lectures. And he's going to be moving our conversation on beyond matrix models to loop equations that actually compute things that matter for the world, namely Wilson loops. And this is only part one of a two-part thing.
Multi-part.
No, not two.
Three.
Multi.
Not three.
N-part thing.
Not three. 4 or 5.
A 4 or 5 part thing. Setting up a path to computing observables in QCD using loop equations. And if you want to interrupt at any point and ask a question, give Rahul, who's sitting next to the water cooler, a chance to come over to you so that you can speak into a microphone so that Sasha can hear what your question is. And it's very, very fancy technology because it beams directly into his amplifier thing in his ears.
I thought you were going to say straight into his brain.
Well, that's right. I have
the next upgrade.
Neuralink, so I have it directly into my brain.
Yeah. I thought so.
So feel free to say anything you like directly into Sasha's brain. And yeah, thank you, Sasha.
Maybe I can also announce that for this week it's on a pizza night. Probably for next week it'll be on a Wednesday, not on a pizza night. So we'll announce when this particular set of lectures happen. But there'll be one a week for as long as it takes. So.
Before I start physics, I want to spend just 2 minutes speaking philosophy, because philosophy is important to understand life and physics. So some people think that history goes in circles. I disagree. It goes in spiral. Let me draw that spiral. So what happens with history is that it repeats itself, but never exactly. It is a helicoid. So 40 years ago, I was desperately trying to solve Planar QCD right after it was born. And I thought I did it, but not completely. And then it was mostly forgotten. And now, after 40 years, I was there. We're now sitting here, right above that point. Now I want to build a little wormhole from that time to here. Because for me, that's an effort to pull myself up to the level. And for you guys, it's a hope to look down and fix up very useful diamonds which are left behind. I think so. Okay. So my lecture will be called Geometric Solutions, Loop Dynamics and Geometric Solution of Planar QCD. So there will be 4 or more lectures, depending on whether I will keep solving, and maybe there will be lecture number 5 or 6. But anyway, today will be loop calculus and MM equation. It's, MM for my former student, Makenka and myself. The equation will be used to generate planar graphs, and also I will describe what's called singularity catastrophe. And the next lecture will be about momentum loop space, which is a natural way out of these paradoxes of loop equations and make them algebraic, which is very important, especially for you guys who are studying these amplitudes and algebraic relations there. So that would be direct, I would say, forgotten past another spiral precursor of these momentum amplitudes. And then there will be next step, which is the thing called Hodge dual minimal surface. That I claim is the correct string model which describes QCD, and not in a sense that it looks beautiful mathematically, but in a sense that it solves the MM equation. See, you don't really need to build beautiful models. You have to solve equations. Equations are there. And then I will finalize that solution on the lecture number 4 by adding certain important element which reproduces planar graphs on that minimal surface. So that's the plan. So today, introduction is that there's the limit of infinite number of colors QCD with thought should correspond to the string theory. That was basic conjecture made by the founders, in my view, mostly by Hooft. But there are other people who were trying to do the same thing, but Hooft formulated that in a very precise way in topological terms. Now, the object which we're going to study, which is a very popular object, but in my view, it is misunderstood and abused, it's called Wilson loop. It's a trace of holonomial, the path integral of exponential of integral of H field around the loop. Now, the goal is to find some string action, something depending on this trajectory, some trajectory x, which is related to loop, and maybe you will represent the Wilson loop in terms of this functional integral with some string action, or maybe you represent directly the physical amplitudes, which I'm going to talk about. But anyway, you want to represent what is observable, which is physical amplitudes, in terms of some stringy path integral. Not necessarily literally the Wilson loop, but the derivatives of Wilson loop, derivatives in a sense that things derived from Wilson loop by certain procedure, which I'm going to describe. Now, the obstacle for that problem is that that equation, which in principle is a correct equation describing QCD, that equation had some singularities. So that's a very stupid obstacle for a modern physicist, but the fact is that that obstacle stopped us for 40 years. And I found embarrassingly simple way around it, which could have been invented, again, 40 years ago. And I hope it will place this loop equation from head to back to feet. Okay, so I'm not going to discuss these obstacles. I'm going to directly switch to my topic, which is Wilson loops and physical amplitudes. And again, when you interrupt me, you kind of make my day. I would be very happy. I'm not afraid. I welcome questions. And maybe I will give you wrong answers. That's another story, but I am not going to be frightened. So please don't be afraid of asking questions. And then I will just pass the mic. So the observable amplitudes, for example, this one I'm talking about is the two-point function of quark bilinears. One is Q bar Q, maybe something in between Q and Q bar and Q, like gamma matrix or derivatives, some local gauge invariant operator. So symbolically, two bilinears, that's an amplitude, which depends on the momentum or coordinate difference. So let's assume momentum. Then there is a formula which in my days was kind of known to practitioners, but maybe now it's forgotten. This amplitude is related to Wilson loop in a very direct way. It is integral, first of all, it's integral over the loop. The loop is represented by velocity. Because everything is translation invariant, it doesn't depend on physical position of the loop, but depends on the velocity of the quark on the loop. It's a proper time trajectory. The velocity is c prime. So you integrate over this velocity, Wilson loop, and here is the exponential. The first term in the exponential, this one is just the external momentum q injected at the point S1 and taken out at the point S2. So if you add this part, that thing will integrate to C of S2 minus C of S1, because V is C prime, so integral dt of V equals difference of C2 and C1. That's called vertex operator. So that's obvious part which you need in this amplitude. And this part is what you get for classical particle. So the first term is a very trivial one. K is a constant vector. So K times integral of V dt is a delta function which guarantees closeness of the loop. You only want to integrate over closed loops. And V squared over 2 is kinetic energy.
So these S2 and S1 are just 2 points on the curve?
Either it's the clouder or you.
Yeah, it's the parameter.
Turn
Oh,
on
yeah, no.
my, sorry.
Well, this was a very trivial question.
Okay.
Why are we integrating over S1 and S2?
Oh, yeah.
Why are we
That's a great-
integrating over S1 and S2?
Why we're integrating over what?
S1 and S2.
Oh, because you see, that's a good question. When integrating it, because originally we had the quark loop in the vacuum, which was a trace of logarithm of determinant. That would be integral ds over s. Then when you insert one point, you will have to integrate over the position of insertion. How to put it? You differentiate logarithm with respect to external current. And if you differentiate the trace of logarithm of inverse operator, you will have integration. There is a formula for this. If you take, how to put it? Originally, there was something like that.
Sasha, where's the loop? I don't see the loop. I see a q bar q.
Loop is C.
But on the left-hand side, we're not just inserting q bar q
Oh, on the
at
left
one
side
point
is
and
is a 2-point amplitude.
Right.
So the formula is like that.
So on the left-hand side, I have q bar.
So that's Q,
Yes.
that's Q, that's
Right.
in momentum Q. This
Yes.
is quark loop. And W of C is amplitude for a quark loop.
Let me just draw, let me just make sure I understand. So I have a q bar q that I insert here. One operator here. I have another q bar q here.
Yes.
But I don't see this. I just see q bar q here and q bar q at x.
And
But I'm
don't you
supposed
know
to
that there is
integrate over
W of
Yeah.
C inside?
W of c inside, which depends on what I mean by drawing.
No,
these
no, no,
lines,
it's
right?
exact formula.
But the data of my problem is just 0 and x. Where is this loop?
No, no,
When I
there is
hit-
Q and minus Q, okay.
Yeah.
So here's the exact formula, trace of log of
Yes.
Dirac operator.
Uh-huh,
And that is shifted by a gauge potential.
uh-huh.
Is integral ds over s. E minus s.
Yes, that's just the
times
log. This is, yes,
Yes.
that's right.
And then that can be written as E minus s times E minus s times Dirac operator can be written in terms of Wilson loop. It is a trace of, well, trace is here, of path exponential integral a d c
Mhm.
over the loop minus integral of c prime squared over 2. When you take that exponential of operator, you could write it as a product of little pieces, and then you have multiple integral over
I'm
infinite
sorry,
space.
I have a much more simple question. I don't see, where's the loop? Where, I mean,
That is Wilson loop.
are you integrating over the loops? Are you
Yes.
integrating over all loops?
Yes.
You're integrating
Yes,
over all
I'm
loops. Oh,
integrating
fine.
over-
The capital DV is the integral over the loops.
Oh.
Okay, that's fine.
okay.
Yeah, so it's the integral
Trace,
over
yes.
all the loops that are anchored to these 2 points. Right. I integrate
Yes,
over
this
all
is
the
a
loops,
loop.
yeah.
Except
Yes,
instead
Loop
of
has
fixing
two
the points.
special
Yes,
points,
that's right.
S1
That's right.
and S2.
That's right.
You fix the momentum, it's in Fourier space.
Yes.
So
And,
It's the K.
and what I was trying to explain how you get integration over S1 and S2.
Yeah.
Because you have also external current. This Q bar Q means there is operator G of S1. There is operator because there is integral over S. So it will be integral G of S ds. So when you find variation with respect to that external current, you will get integration over S because it is here. Everything is integrated. So when you have delta delta external current at a point, it will be integral ds1, and then there will be this, and then another one. You have another delta delta j to bring down another quark current. You'll get the integral ds1 ds2, and then there will be u s1 to s2 times u of s2 to s1. You see, there will be a loop. This loop, which is in a vacuum, doesn't have extra integration. But when you find variation with respect to external currents, you get this integral over S because it was there here. In the exponential, there is integral. So when you find variation, this formula, I'm sure, is in textbooks. Maybe those are very dusty textbooks which you don't read anymore. But that's the formula which you derive from definition of the vacuum energy as trace log of determinant. Take trace log of quark determinant, you introduce extra currents, which would add something to this Dirac operator, and then you vary with respect to position of these extra currents, and then you will get integral ds with some delta function, which would then translate into additional momentum added to the loop. So I derived that formula in my book, in my works, old works, but anybody could take standard formula for Dirac operator and reconstruct it as an exercise. Just trust me, it's a correct formula, and it's physically very clear. It satisfies the idea of superposition principle. Amplitude is sum over histories, and amplitude for history is product of amplitudes for events. So this explanation, this path exponential is exactly what it is. So you have product of little events on the history. Event is a propagation from point S to point S plus ds. And amplitude for event is e to the to velocity.
I was just trying to understand where you're integrating over all C's. There's not a fixed C. You're integrating over all C's.
I mean, it's not me.
No, I know.
It is what trace does. Trace means you have to sum over all intermediate states, right?
Yeah.
You sum over history, and history is product of events. Each event corresponds to a little shift in the coordinate. And that's why you have functional integration over loops, because you're integrating over all these internal positions. Functional integral over loops comes because of trace. Okay.
Okay, very good.
So this formula is kind of the basic formula you have to understand when you want to relate Wilson loop to observables. All observables are like that. You could take 4-point amplitude, scattering amplitude. There will be just 4 points and 4 external momenta. It's very easily generalizable. It will be always path integrals over the loops. And the weight will be something like that. And the difference will be there will be not one external momentum Q, but several. So this term is characteristic for the external momentum, which is injected in point S1 and taken out in point S2. For the 4-point amplitude, there will be several momenta corresponding to the 3 channels of the 2 channels, whatever amplitude. So it's a very easily generalizable formula, but it always involves integral over loops. Now, I, for simplicity, ignored the spin of the quarks. So that is a formula for scalar quarks. Later, I will describe correct formulas for spinor quarks. They are more sophisticated, but the physics is the same.
Yes.
It's just there will be some, yes.
Could you repeat what is
I'll give
K?
him the,
Could you repeat what is K in this formula?
It's Q.
K is the, well, you could take K out of the integral. It's K times integral of V over closed loop. And when you integrate over K of something, it gives you delta function. And that delta function ensures that the loop is closed. Integral of V around the loop must be 0.
Is Q the momentum of the correlation function on the right?
Precisely, that's right. Like I described here, at the moment S1, Q is injected, at the moment S2, it is taken out. So Q and minus Q, because integral dV, dt of V equals difference, so integral Q times integral dt of V from 1 to 2 is just Q times S C of S2 minus C of S1. In the language which you know, it corresponds to vertex operator. E to the I Q times position of the vertex. But I prefer to write everything in terms of G, because in that representation, all functional integrals are absolutely elementary, because if you replace everything in terms of v, integrals are elementary. It's Gaussian integral. There are no derivatives of v. So it's a local integral, absolutely trivial local integral. When you integrate over v, you get Gaussian, and then you will integrate over S1 and S2. So after integration over v, if W of C equal 1, of course. If W of C equal 1, how we reproduce the ordinary quark loop? I think I reproduce it later in this. Okay, let me first tell you how I reproduce the ordinary quark loop. If W of C equal 1, then this path integral is Gaussian. Gaussian integral is trivial because there is no derivative of v. It's just v at any given point. So at any given point between S1 and S2, it's just this v here, and v squared here. Result is Gaussian. You will get some trivial k plus q squared. So there will be something like that. When you will get something like that, k plus q squared times S2 minus S1, because between S1 and S2, there are both k and q, plus k squared times S1. So when you integrate over this difference and this difference, you will get 1 over k squared from here, and 1 over k plus q squared here, and you will have integral d for k. And that's what people call quark loop. You'll get these Feynman propagators. You see what I'm describing? Integral over velocity is absolutely trivial because you have to just split the integral over S1 and S2 from the complete integral to the difference. So S1 minus S2 is 1 positive variable, which I call, let's call it S3. So you will get integral ds3 from 0 to infinity, e minus S3 k plus q squared times integral ds1 from 0 to infinity, e minus k squared s1. So this one gives this denominator, this one gives this denominator. End of story. That's how Feynman graphs are recovered from this representation.
So when the Wilson loop is 1, you just get the Schwinger parameterization. I thought so. Anyway, this is it. So you're just saying when the Wilson loop is 1, so when there's no thing out front, then you just get the Schwinger representation for the bubble, right?
That's right. Yeah. I'm just it's a trivial case when W is 1, no functional integration left, everything elementary. But when W is not 1, when W is sum of planar graphs in each order, again, the path integration will also be elementary. In each order, it will be also elementary. For example, here's perturbation theory for W. So first order W equals 1. Next order, it is one gluon graph. And I prefer to write one gluon graph like that. It is something is missing here, maybe. No.
Where's the problem?
Something is missing. There is 1 over.
There's a 1 over.
1 over
S1
p
minus
squared
S2
or
squared.
something
Yeah,
like
that's
that.
propagator missing.
Huh?
1 over S1 minus S2. I mean, you have to.
No. 1 over p squared, I guess. No.
Yeah, here's 1 over p squared. Yes, that's right. Yeah.
Whatever. Something like that. When you substitute that, you will again integrate over Gaussian integrals, and you will get this diagram. So that's the first diagram which you get, and then in this order you will get the next diagram. So in the next order you will get this diagram plus this diagram plus, so there will get actually two diagrams. If you take the next approximation for W, this double integral, then depending on the time, there will be integration variables in the Wilson loop. I call them as one, but they better be called T1 and T2. They're different from that one. So there is now, you see, there is now S1, S2, T1, T2. And depending on the integration region for T1 and T2, you'll get either this diagram or this diagram. Yes?
Is it obvious that it's actually a Wilson loop and not products of two Wilson lines?
What do you mean? Oh, it's a trace.
I'm just asking if there are no UV stuff that you need to care about when you call it a Wilson loop.
It is trace of path exponential. Yes, it's the definition. That's what you derive from representation of the Dirac operator. From the Dirac operator, you get Wilson loop by definition. That's exact formula. Because that the most elementary formula is that you have, if there is no internal quark pairs in the vacuum, then quarks are just moving in external gauge field. And amplitude for a quark moving in external gauge field for a given path, amplitude is amplitude for a free Dirac particle times a trace exponential of gauge field.
I'm not sure about it, but at next order, the operator QQ bar would have some corrections.
Next order of what?
In perturbation.
It is always the same formula with W of C. And perturbation theory means that W of C is not just one, but there are all corrections are corrections for W of C. W of C is expectation value in presence of quantum gauge field. So W of C by itself is sum of planar diagrams. W of C is expectation value of ordered exponential integral A dx over the loop C, expectation value for the gluon vacuum. So you take the glue dynamics, which is weight E minus integral F squared over G naught squared, and then you take that and make expectation value of path of the path exponential of gauge field with respect to the QCD with the glue dynamics amplitude.
Can I just ask?
Explain it in.
No, I don't want to explain. I just want to ask. So is the claim that this is also somehow integral over all C?
This is
sorry. Is the claim that it's somehow
over all
integral over all? Sorry, but integral over all. This is what I'm asking. Are you saying integral over all C of WC is e to the minus trace log d slash?
Yes.
That's what you're saying?
Plus
in other words, this is like
S over
this is
F.
yeah, right. But this is some first quantized picture, right? That like if I think about if I think about getting e to the minus trace log d slash from integrating out the quarks, I can also think about integrating over all the paths that the quark could take and summing over all those possible curves.
Yeah, trace exponential.
Yes.
No, not exponential. Trace of
Directly. Just this is log det. This is just this
because
is
there are no
log d
internal.
slash.
That's one trace. It's vacuum energy.
So this is somehow the now what is the definition? This is a stupid question. I mean, how exactly do you define this path integral over all curves? What's the definition of this path integral over all curves?
What's beneficial?
What's the definition? How do you define it?
Oh, I just defined to you. It's product of S dV.
Oh, okay. So you
Of
just
S.
okay, fine.
Times
Okay, that's fine.
delta
Okay,
function
that's fine.
of sum
Okay.
ds d of S.
But it's like
It's just linear measure.
so when we do the path integral over the quarks, we get the determinant of d slash. That's the sort of field picture for integrating out the quarks. But there's also kind of particle picture for integrating out over all the possible trajectories of the quarks.
Yes.
And that gives you.
And that's
this
a very
identity.
important element which I wanted to bring into the discussion because it's often forgotten. People think that WFC is something which is observable. No, this is what is observable.
Okay.
And paths which are relevant here are not smooth. So trying to make W for smooth path finite is the same as painting the chairs in the Titanic before the crash. Useful, but not very. Okay, so let me go for. I promised to my AI never joke like that in lectures. My AI advised me to be very politically correct, don't say anything bad, but I hope you'll forgive me. I will keep doing that. So velocity distribution being Gaussian, as we saw, it is Gaussian. These paths are Brownian with infinitely many cuts. They're not smooth. And the fact that they are not smooth has very specific consequences. After this path integration, there are new divergences. You see, say you take W equal 1, perfectly finite thing, but then you integrate over paths, you get a quark loop which has a logarithmic divergence. So, or vice versa, you take the W with several more gluon graphs inside, it has some singularities, but when you integrate that out and look at the 2-point function, it doesn't have those singularities, it's a totally different singularity. So singularities of the Wilson loop or smooth loop are irrelevant because they either integrated out or they don't apply because the relevant paths are not piecewise constant. They're Gaussian. Anyway, so this Wilson path integral leads to new divergences. And so Wilson loop integrate over path given set of external momenta injected creates observable momentum amplitudes, which are renormalizable, by the way. That is what is renormalizable. For example, the 2-point function of 2 electromagnetic currents, it doesn't need renormalization at all because the currents are conserved, there is no divergences. So that's something which is just have one trivial overall divergency. And if you take, say, imaginary part, which is cross-section of the E plus, E minus annihilation, then it is simply finite. It doesn't need any renormalization. So Wilson loop doesn't tell the whole story. Now, so that was the introductory number 1. That was the crumb for you to bend down and bring from the wormhole to the 40 years back history a little piece that observables are path integrals and exactly over Brownian paths. So you have to be very careful about renormalization. But that also means that we could compute them, Gaussian integrals or non-Gaussian integrals. In the end, as I will describe you, that same formula for the quark amplitudes would be used to compute them, literally. Now, second identity, which again is too simple to be understood, is what I call holonomy identity. I write it down, and it looks so familiar, but you would think I made a typo, but I didn't. So let me explain what it is. So path-ordered exponential of covariant derivative operator along the closed loop is equal to the Wilson loop times identity operator in Hilbert space. So on the left, we have something like that. We take a loop which have a point x. So at some moment theta naught or equal to 0, the position is x. And then there is loop which starts with x, goes around, and ends with x. So take that loop and take path exponential of integral around the loop. So d theta c dot is just element of the loop. And multiply it not by the something depending on the point on the loop, but something which is just dependent on the initial point. So d mu of x is not what is on the right. On the right is gauge field at the position C of theta, but on the left is just the operator at the arbitrary point, which is the beginning of the loop. We take a covariant operator, which is just operator, and as operator, you translate it around the loop and come back. I claim that such an integral, which was studied by a mathematician, relevant thing is called Magnus expansion and Magnus representation. So you take just some matrix or operator and translate it around the loop. So because this matrix has several components, mu is not just one component. So it doesn't, different components don't commute with each other, and that's why this path integral is not a trivial thing. It would be totally trivial if it would be one-dimensional. If you take one-dimensional just matrix and integrate it around the loop, you will get something very trivial, of course. You will get this matrix times integral over the loop, which is 0, so you'll get unity. However, in case when different components of this matrix or operator don't commute with each other, you get something non-trivial. What I claim is this non-trivial thing, 1 is gauge invariant, and 2 is proportional to what we call Wilson loop. And the coefficient is just mathematically, it's unit operator in Hilbert space because d mu is a covariant derivative operator. It works in Hilbert space. So that's exact formula. So path exponential of
What is the covariant derivative? Sorry, is the covariant? I don't understand what the covariant derivative. I don't understand what the covariant derivative operator
great
is.
question. I'm not ashamed of explaining that. And you shouldn't be ashamed of asking because there is no such thing as stupid question. There is only stupid silence.
Yeah, don't feel ashamed, Dave.
Sorry, are you talking about, is this partial derivative plus a mu?
Yes, exactly.
Oh, that's it. Okay.
Exactly. It's partial derivative plus a mu. No. I have to be very specific.
But at one point,
Yeah,
That's
I
right.
understand. There's just.
if there's no gauge
d
field, it's
mu
obvious,
of
right?
x
If there's no gauge field, this is
equals
just
d
one.
mu
because
Yeah, I
it's just
plus
even-
a mu
I just didn't realize.
at this point x. So in my case, I'm taking d mu at one specific point. So a mu is sitting at the arbitrary point x. And somehow magically after path integration, it will become shifted to holonomial as it should.
2 questions. These are stupid questions.
No. I am saying there is no such thing as.
Trust me, this is stupid.
Yeah.
The mu x, can we take it outside of the integral?
What do you mean outside?
On the left, I mean, it does not
No.
depend on.
X is a point at the loop.
Right, so it doesn't depend on theta, so we can move it outside of the integral over theta.
What can we?
No, because it's.
No, we
no,
cannot
no,
because there is
can be-
more
it's
than
a
one
path ordered
component
exponential.
of d mu.
Okay.
It's a path ordered
The trick is it is a vector operator. If it would be if mu would be only one component, we could indeed take it off.
Okay.
The whole thing is non-trivial because various components of d mu don't commute with each other. It's called curvature.
Gotcha. And what is the Hilbert space that you're referring to? Yes.
The same space where operator d mu acts. It acts on the space of covariant of the matrices of coordinate of the functions of coordinate. It takes
acts on the
actually
field.
it is a space of gauge fields. But in this particular case, it's unit operator, so it does not change when you do gauge transformations.
I guess if we move x infinitesimally, it's clear that we get the same operator because the difference is f mu nu contracted into the velocity field and you get 0.
Well, we could verify that formula, of course, by expanding a mu in terms of the local expansion with f mu nu, and for small loop, you will of course get identity. On the left, you will get commutators,
Right.
and on the right, you will get
Yeah,
commutators.
but that, I guess, exactly. But I just want to say a little bit more quickly. Just
Give me back
Oh.
my phone.
Just even see that this thing does not depend on x. On the left, on the right hand side, we have the Wilson loop. On the left hand side, it does not depend on the point x, right? I mean, the light naively depends on the point x.
Well,
but the
that's
answer
right.
does not
It
depend
is.
on the
That's
point
right.
x. And the reason it doesn't depend on the point x is that if you move x slightly, the difference at this order is, V mu,
Backtracking.
V nu, F mu nu, and it gives 0 because F mu nu is antisymmetric.
No. It's much simpler than that. The trace doesn't depend on the initial point. That's why.
But d mu of x, I mean, the left-hand side has some dependence on x. So if I move x slightly, I'm trying to understand the simple reason why this operator does not depend on x.
If you move slightly while keeping it on the loop,
Yes,
then that would be.
then I think that's just F mu nu, but.
That would also
contracted
change
into F mu nu.
definition of the right. That integral of the right is. If I don't take the trace, if I take the trace, it doesn't matter.
Right.
If I do take the trace, you should integrate on the right from that point theta naught where x sits. You see?
Oh,
but
no, I mean, after the trace, yes, after the trace.
After the trace,
Yes,
it will
yes.
be invariant. Before the trace, it
No,
will
it's
be path integral.
Sure, yes.
Integral from theta naught
Yes.
to theta naught plus
Okay.
2 pi of a d a,
Mhm.
well, a of c
Yeah.
of theta d c prime d theta.
Yeah.
So when you move theta naught, it is
Yeah.
so, the right side also change. But if I take a trace, it does not change because trace doesn't depend on the initial point. Okay, so let me derive this formula. Now I'm going to bore you to death because I will actually derive this formula. And that's important to understand how that magic happens. So please follow me. Or if it's trivial, just take a nap. But anyway, so the definition of path exponential is product of little exponentials, right? Ordered product of terms which each has exponential of delta theta times this thing. And they, of course, don't commute with each other. That's the whole thing. Because directions of the path are different, therefore, next to each other will be operator involving different components of operator d mu. Now, we do something again very obvious. Exponential of, we just split the operator into two terms, and then up to the theta squared, it will be just this thing, which is translation operator, times this thing, which is indeed a non-trivial thing, which is an operator in gauge space, right? This is the factor which is non-trivial, as non-trivial, it's element of the gauge group, and this one is just the translation operator, which just translates arguments of the functions by a certain amount. Now, yeah, that's what I tried to say. Again, I'm sorry, that's insultingly elementary, but it is. So this operator T, which is a translation operator, T, it moves argument of everything which is to the right. And it is non-trivial because there are products of these operators and each one doesn't see what is on the left and only shifts whatever is on the right. So when you do that, you'll find out that you could move that operator past this one at expense of changing argument of A. So there's this hopping identity, you could move it. And then you keep doing it. So when you take this operator and move it through all the factors to the right, you shift all the factors by only one element, by this one, DC. But then you keep doing that. And then what you find out, of course, is that you could, for the operator A in a position K, you will shift its argument by everybody who was to the left. So that will exactly give that A the argument on the loop. And then in the end, so that's what you will get. And then in the end, you will have all the operators A with correct arguments, and then you will still have an operator exponential of sum of delta C times D. But if the loop is closed, that sum equals to 0. Therefore, it's a unit operator. So you will get a local limit what we need, which is Wilson loop, times exponential, which looks scary, but but actually it's not so scary. It is just operator of shift by total difference between the endpoints, and if there is no difference, then that is a trivial shift operator equals 1. So we have proven that identity. Now, why did we need that exercise? What was wrong with original formula? Why did we make that effort? Because in the original formula, the loop was involved in 2 places. It was velocity of the loop in front of a mu, and argument of the gauge field was c, and c is integral of velocity. So variation with respect to c of original Wilson loop is non-trivial exercise, and people struggled through that. There was so-called Mandelstam identity, who first collected the terms. You could do it by integration, by part, and variation analysis. So, and then that led people to all these singular expressions. So what I'm trying to say is that with this operator representation, it's again embarrassingly simple, because what you have is something which has C prime or C dot only in one place. So when you find variation with respect to C dot, you simply bring down the operator covariant derivative at that point. So it's as simple as it gets. You could do it many times. Every time you find variation with respect to C dot, you bring down d mu. And of course, when you bring down d mu, this thing is no longer the unit operator, because this d mu acts on everything to the right. So this by itself is still an operator. This is a bad thing. So variation with respect to C dot is actually not a C number, because it involves operator d mu. This thing on the right is proportional, as we have shown, to unit operator, but this operator is not unit operator. So this is still an operator. However, if you take 2 such derivatives and take antisymmetric part, then this product of d mu, it will become commutator. And once it's commutator, it's no longer operator of derivative, it's just C number. So once you take second derivative with respect to C dot and then symmetrize it with respect to vector indices, that's when you get F mu. So the simple way to get gauge field objects from the Wilson loop in this representation is just anti-symmetrizing with respect to the tensor indices. That immediately makes transform derivatives in commutators, and then you will get what you want, which is F mu times Wilson loop. So that operator is called array derivative. That's an operator which being this operator on the right, when you apply it to a Wilson loop, you will get Wilson loop with F mu inserted. Is that clear? Anybody who is doubting, please ask me questions. Maybe I lost you.
If you write the Wilson loop as an area.
Give him,
then it's
please.
obvious, right? If you write the Wilson loop as a two-dimensional integral of F mu, then
There is no such thing for non-abelian theory, unfortunately.
but this sum was still satisfied?
That's right.
So what's the explanation?
I just derived it to you.
What's the intuition of this result?
Well, you could write very complicated surface integral there is a version of Stokes theorem where each point inside the surface is back translated to original point by little wires. You could write a totally crazy Stokes theorem, but that's useless because this thing is much better. You don't need to use Stokes theorem because you have trivial formula. Your Wilson loop is expressed in terms of it's called Magnus integral, exponential of a fixed matrix. When you find the derivative, it's absolutely elementary. So I avoided that problem of Stokes theorem.
I have just a stupid confusion. So the whole point is that the only place the gauge field appears here is at one point, right? Is at the point X. That's
right.
So can't what if my Wilson loop for a while is pointed in the Z direction, then it bends, does whatever else. And my point X is, however, on the spot where the Wilson loop is pointing in the Z direction. Can't I go to a gauge like, AZ equals 0 gauge?
Oh, you could do
And
much
then-
simpler. You
yeah.
could go to Schwinger gauge. You say A mu equals F mu nu, A mu, which is constant, which is drops, F mu nu, X nu. That's the simplest gauge where you could derive everything.
Well, no, I'm not trying to, yes, we could also do that, but I have a different question. Why doesn't that make it seem like, if I'm now imagining shoving this into a path integral, it looks like A mu just disappears entirely from this object.
As it should, because it's not gauge invariant.
I know, but,
But it's dotted with
yeah.
the C dot vector, right?
That's fine, but
So
my C dot vector is in the direction, I mean,
But
it's
then
in
the
the
C
Z
dot
direction
vector
and
changes
it's huh?
as you go around the C dot vector.
That I understand, but d mu, but d mu is only inserted at one spot, right? I
D
see,
mu
I see.
is-
Somewhere else, it's gonna turn around, yeah,
Yeah,
it's
it
not
is
very
moved
local
around.
seeming.
It's
Okay.
moved around. That's the whole thing.
yeah, I see.
I just proved to you if you take
Yes, yes.
operator derivative, because it involves operator and exponent and move around, it automatically shifts
Yeah.
its own argument.
Yeah.
That's the whole thing. Okay. So that is very important. Now we can easily derive, for example, here is the what I call loop diffusion operator. The operator which inserts the equations of motion. That's not a joke. That's something very important. Here is the operator. I just wrote it here for you, which brings down from the Wilson loop exactly the expression which corresponds to the gauge field equations of motion. And that's the idea behind the equation. You find the loop variation operator, which brings down equations of motion and say, aha, if it's equation of motion, then it's equivalent to certain commutators or whatever. Average of the Wilson loop with equation of motion is equivalent to variation of Wilson loop. It's called Schwinger-Dyson equation. And that is how the equation is derived. So to get the loop equation, you first find the loop operator, which brings down this d mu f mu nu. So commutator d mu d nu is f mu nu. Commutator of d mu and f mu nu is exactly the equations of motion. So here is this operator. And notice that this operator is a third order in the derivatives, because area derivative, this delta delta sigma, is second derivative with respect to c, right? And you take derivative with respect to c dot and then symmetrize, and then you take another one, but you apply it before and after this angle. That makes it a commutator, because it doesn't just need the d mu, you need the commutator. Commutator in this language is imitated by changing ordering of points, right? Because we have ordered integrals. So if you take delta delta c dot to the right and subtract delta 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 c dot to the left, that would just create commutator. You see, delta delta sigma creates something. Now, when you apply further operator delta delta c dot of the argument theta, which is slightly to the right of the argument of this one, that means that in the ordered product, which was Wilson loop, I'll bring down operator d mu not at the point theta, but at the point theta plus 0. And that, and if I do with this same derivative shifted backwards, I will get before. So the difference between these two, or this continuity, will effectively create commutator. So this continuity of the dot derivative is equivalent to the commutator. So now we derive a very important thing. We derive nice non-singular expression for the loop operator in terms of what I call dot derivative. So all you need to do if you want to test your expression or verify your string theory, you need to find this multiple derivative with respect to the velocity of the loop in certain order and symmetrize them, and then you will get the QCD equations of motion. So that's a very important bridge between gauge theory and loop space. Here is operator in loop space, which is totally gauge invariant. I mean, it doesn't even know about gauge. It's just a manipulation of its functional derivative with respect to the velocity of the loop. So you take third functional derivative, and you will get in the end now. So I call it operator L, loop diffusion operator. So that's a certain combination of the third functional derivative with respect to velocity of the loop. It is basically third derivative with respect to the loop, anti-symmetrized with respect to tensor indices and contracted with a couple of indices. So in symmetrized between these two, then you contract with this one, and that's how you get it. But basically, it's all, this operator L, by the way, can also be written as something much more explicit. This operator L can also be written as following. L, it has index nu, and then can be written as P alpha beta gamma nu times delta C dot alpha delta C dot beta delta C dot gamma. So you have third functional derivative of points theta minus 0, theta plus 0. You have three consecutive points. In certain tensor, which is extremely simple, T alpha beta gamma nu equals something like delta alpha nu delta delta alpha delta alpha gamma delta beta nu minus well, there was plus, it is minus something like delta alpha gamma delta. Oh, it couldn't have beta. Oh no, beta nu alpha gamma. I don't remember. There are some deltas. It is in the text. Delta alpha, delta beta gamma, delta alpha nu minus 2 other deltas. So there is a combination of three deltas with coefficients which correspond to this thing being antisymmetric with this beta. Oh, it is antisymmetric with respect to beta and gamma. So it is it is not antisymmetric with respect to alpha. So it's only antisymmetric.
Delta nu beta, delta alpha gamma minus antisymmetrized beta gamma.
Yeah. So basically, it is this thing properly antisymmetrized. So there is delta of alpha gamma beta nu antisymmetrized with respect to beta and gamma. Yeah, something like that. So
I'm a little confused by one thing. So you're saying it's sort of you want to rewrite the Wilson loop instead of as something manifestly local. You want to write it in a way that looks like you're taking the operator here, but you're averaging it around the loop in some way, right?
I needed that formula only to be able to derive the loop equation operator, because otherwise it will be complicated. I could derive it ordinary way.
Is it going to matter to you to represent the Wilson loop in this way rather than the conventional way? Does it matter for anything else?
No, it just simplifies the derivation of the loop operator.
Okay.
If you make an effort and do all the functional derivatives and in the end correct the terms, you will get the same expression, of course. You could use ordinary functional analysis using the operator, using gauge field, ordinary Wilson loop.
But
Or
this
C is inside.
no, that's fine. But this is not making the Wilson loop any more or less, I mean, it's the
It's
same operator.
identity,
It's identical.
it's identity. This identity allows you to, a shortcut to
That's
this
fine.
formula, which of course can be checked using this Schwinger gauge for A mu.
Mhm.
Yeah. But you see, it's important because for 40 years, people didn't know that. That formula, with all its triviality, is new. And that is a key to the momentum loop equation. It's a key to many, many things. It's a key to this exact solution, which I'm going to present later. Because when you write down original wave, which people wrote for 40 years, there are all kinds of delta functions and singularities which have to be canceled and not confused with ultraviolet singularities. So people were really confused because this is a classical expression. This has nothing to do with ultraviolet. All these limits of theta plus 0, theta minus 0 are not related to singularities. They are true for the simply constant gauge field. Take constant gauge field and try to consider order exponential. If it is constant gauge field, just matrix, 4 different matrices, it still have F mu. So even for constant gauge field without any ultraviolet divergence at all, this limits still non-trivial. You have to take the limits from that 0, minus 0, you have to order points. It reflects the fact that we are trying to present something which is internally 4-dimensional by means of 1-dimensional topic. We are using 1-dimensional loop to represent something which depends on the whole 4-dimensional field. Therefore, we have to move loops in different directions, and these different derivatives don't coincide for purely kinematical reasons. So this formula is not singular. It's just the fact of life that left and right derivatives are different because the components don't commute. Okay, the beautiful property of this operator L. It's so-called Leibniz property. If you take product of 2 arbitrary functionals and apply operator A, it works as if L is a linear operator. You see, L, in fact, is a 3rd order operator, but a very special one with this anti-symmetrization and this limits theta plus minus 0, so all regular terms cancel. So this operator obeys this Leibniz property. It works as if it is just a linear operator. And it also obeys second Leibniz property is you apply a function, ordinary function of some functional, it will be the same operator applied to the A of C times F prime.
Is the intuition why this 3rd order operator acts like a 1st order operator, that the first 2 basically bring down an F nu, so it acts sort of like a C number? Is that sort of the...
Yes, you may say so, but you may also say that in general, the 3rd functional derivative is symmetric with respect to all 3 indices. But I'm taking specific anti-symmetric parts. Now, if you try to apply the general Leibniz rule, you'll find out that terms which don't obey Leibniz property are symmetric. So if you anti-symmetrize, you cancel those terms. So this anti-symmetrization, the same one which brings F mu, is the result. So this is a very singular combination of 3rd derivative.
Yeah.
Typically, a 3rd derivative is symmetric with respect to arguments. But since there are 2 arguments now, angle and nu, so symmetric with respect to complete interchange of argument C nu and another argument theta nu, another theta prime nu prime. So it is symmetric with respect to complete interchange, which means it could be symmetric with respect to both or anti-symmetric with respect to both. So we're picking the term which is anti-symmetric because we are anti-symmetrizing with respect to indices, and therefore we're picking something which is anti-symmetric with respect to angles, and that's something local.
Sorry, I just want to sorry, I think there will be a clarifying question for me. So you're saying the key property of L is that it relies on the equations of motion? Like it
No, at the moment I said nothing about it.
Okay, so that everything is true here, even if I added an FQ
It's a
term.
purely kinematical statement.
Yeah, okay.
It's because it's triple commutator, that's it.
Okay.
It's because it is equivalent to triple commutator.
Yeah. So so you'll get to later where the dynamics are entering here.
That's right.
Okay.
And that later will be very soon. by the way, this Leibniz property allows to prove very important thing, which will be in lecture number 3, which is you could solve, it's called invariance or whatever. So Wilson loop, if you find the perturbative Wilson loop which satisfies loop equation, then if you multiply it by exponential of something, I call it area, which is a zero mode of the L operator, then you could still have a solution. So solution of the loop equation is determined modulo exponential of minus zero mode of that equation. And that's very important because in 4 dimensions, zero mode exists. And that's related to self-duality. That's a very important thing. So in general, there is no zero mode. But there is a very special reason, Hodge duality, in which case it could prove the existence of zero mode, which is very similar to instant on. So let me skip some calculations. And that is actually indeed this MM equation. You see, I usually call it MM equation, but I don't want you to forget my good old student Makienko, so I have to say it once. Yuri Makienko was my grad student at the moment in the late 70s when we derived it, and he played an important role. I was waving hands and giving intuition, but he did all the precise calculation and in particular the planar graph. So no, he was 100% collaborator, and I'm very happy that he did it. Anyway, so here is this equation. If you look at that equation, it's very interesting. First of all, it's closed expression. It's very precise and closed expression. Let me explain what it means. On the left, it has that same operator we just discussed. Operator which brings down d mu f mu nu. And on the right is a result of Schwinger-Dyson, which is variation of Wilson loop with respect to gauge field at one point. And that integral, it gets delta 4-dimensional delta function of x minus y. It's because functional derivative of a of y with respect to a of x equals delta function. In your matrix models, we have similar matrix equations, but you don't have 4-dimensional delta function because you have only one object. Here, you have a gauge field which depends on the point x, and when you integrate over Wilson loop, you want to find variation with respect to gauge field of in a point x, but in the Wilson loop, it's integrated over the loop, and there is some point y. And that brings 4-dimensional delta function. So you get a very crazy thing. You get 4-dimensional delta function, and then you get line integral. Oh, I think something is wrong here. Oh no, it's correct. This L is defined already with this integration. Yeah, then it's correct. It's a scalar operator. So that's right. You have double loop integral and 4-dimensional delta function, which means the right side is not a number. Right side is a distribution. If you take 4-dimensional delta function and integrate in the tangent plane where loops intersect, you will get solution for the intersection, and then you will get 3-dimensional delta function of transverse coordinates. So this thing is not a number. That's a distribution. And that's important to understand. You have to understand that you're not supposed to have Wilson loop finite. Wilson loop is integrated out with Brownian path. And when you do that, that delta function will disappear. So you don't want to make W finite too early. So here you cannot make it finite. On the right, there's infinity. Now, what is Cxy and Cyx? Well, the loop here.
Sorry, could you repeat when does it blow up on the right?
Where's my phone?
Sorry, it's here. Could you say it again? So in this case, when does it blow up on the right? Like when I mean, of course, there's the delta function.
Yeah. Let me explain. That's a very subtle point. That's not a trivial. That's not even a trivial question. Not just it is not stupid, but it's also very non-trivial. And let me thank you for this question. Okay. So here it is. Here is the loop. So there's point X. Well, you should imagine that this goes like that. So there's point X on the loop, and there's another point Y, right? So so C, suppose loop goes this way. So this is loop CYX from Y to X. And this is loop CXY from X to Y. Now there is this, you may actually write it like that. There is this four-dimensional delta function which attracts point X to point Y. So by virtue of this delta function, both loops are closed. I wrote it like that. So it's actually X. So it's CYX and that's a CXY. So both loops are closed by virtue of delta function. But we have one line integral, right? So when you integrate over one line, you could integrate over longitudinal part and transverse part. Longitudinal part will remove the integration over the line, but there will be still delta function of transverse part of the loop. So it will be non-trivial function of the loop in the vicinity of, it basically must be flat or something like that. There should be no perpendicular components. Otherwise, you should expand loop near this intersection to next order. Otherwise, you will get triviality. And that next order should vanish also. So it would be like C prime C of X plus C prime times delta theta plus C prime prime times delta theta squared, etc. So this term will immediately get compensated by the integral over the loop. But then there will be this term left. And that is also there. So you basically get something like delta function of C2 primes, etc., etc. So you will, this delta function, in fact, is not an ordinary function. It's a functional, really. It is something which shouldn't be understood as a number, but as a distribution. And the best way to deal with that is to go to Fourier, where it becomes a number. Namely, number called 1. So the left side, you have this loop diffusion operator. On the right side, you have this loop splitting. And you have this factorization. Now, factorization is something which you guys know very well without me. We discussed it many, many times. It's just gauge invariant traces factorized. So if you have expectation value of product of two traces, it's basically central limit theorem. You have many several phase term, like sum of e to the I alpha over many alphas. It is basically becomes expectation value because each term is the order of 1, and if there are n of these terms, the correlation is negligible compared to the expectation value. So roughly speaking, that is the central limit theorem for large n. That's something which basically was the main contribution of our paper with McCain, this factorization. And then it was applied to lattice equations, and there was all these Iguchi-Kawai models and other models, which unfortunately led to nowhere because there are lattice artifacts. But this equation stays. It's just a mysterious equation which needs some thinking before you could solve it. So that's how we write it. So operator L applied to W1 equals integral of product of 2W1 times this double line, which corresponds to delta function.
And that's X and Y are the two points on that.
Whereas
It's fine. It's fine. So your X and Y are the 2 points along that curve, and you're splitting it along.
that's right. They are, in fact, far away on the loop, but close in space. So it's planar diagram, so they look very far because they indeed have different angles on the loop. But this double line is very short in physical space. Double line is very far away in the target in the theta space in the unit circle where we're describing this, but in physical space because of delta function, it's
Yes.
Okay, now let me explain. That will be the last part of this today talk. I will explain to you how you get perturbation theory, planar graphs, including Fadeev-Popov loops, etc., by direct iterations of this equation. It is important to understand that not only planar graphs satisfy this equation, but you don't need to do any gauge fixing, Fadeev-Popov, and you don't need to apply to functional integrals. You could directly iterate this equation. So once you have this equation by itself, it produces the planar graph. So you don't need to add any more hypothesis or technology to this equation. This equation itself is sufficient to generate planar graphs. And that's something which we derived with mechanical. And let me sketch how it happens. So we start with W equal 1. So we go back to this equation. We start with W equal 1. So first, say, take each W equal 1 here, and then you will have next correction to W on the left. That's iteration. There's coupling constant in front here, which I didn't write. So the zero order of that constant, W equal 1, because L times 1 equals 0. Of course, W equal 1 is a solution of the loop operator. I would say, by the way, that path exponential of any classical field, like instanton, would be also a solution to the loop equation. You have to keep in mind that W equal 1 is not the only solution of the classical equation, because, for example, we know that any multi-instanton would also solve the loop equation, and therefore you have to be very careful about that.
Wait, I have a quick question before we do the full planar graphs. So this is the meat of the statements you're making, because this loop equation is what contains the dynamics of the theory, like
Yes.
this factorization formula. Sorry, just so I can build, like, what happens if I correct it by f cubed? If I take my Yang-Mills equation and I correct it by f cubed, how does this,
Well, if you don't break gauge invariance.
Yeah, I don't break gauge invariance, so I just get like some additional fudge factor
Yeah,
multiplying.
you
it.
will get some ugly extra terms, but planarity will not change.
Yeah, planarity doesn't change.
No, it will just get some ugly
It's
extra
like
terms.
functional
but-
thing,
Yes.
multiplying the two loops.
Look, can tell you what will happen. The left side is something which depends on your Lagrangian, because L is designed to imitate d mu f mu.
Yeah.
So if your Lagrangian has extra term, the operator L will change. You will have to bring down extra terms from
Okay.
it. But the right side will be the same.
Okay, so it's, okay, I understand.
Right side is simply kinematical formula. It's called Schwinger equation. You take
Yeah,
Wilson
yeah,
loop
I
and
understand.
vary it with respect to gauge field.
Yeah.
So right side will be the same, but L operator will contain extra terms because of extra terms with Lagrangian. And by the way, coupling constant usually enters in front of the f minus square. That's why it is in denominator here, and here it will become in numerator. Okay. So start with W equal 1, and then inversion of this. So how do we generate the planar graph? You have to invert operator L, right? See, here is unknown W2. What is W2? Well, next, L times this unknown W2 will be equal to the right side. Now, right side is a very trivial, because if you take W equal 1, you will get just loop integral of delta function. So L, you look for W2 as a loop integral of some unknown propagator. Then you apply operator L, and you'll find, not surprisingly, that it reduces to the operator, Laplace operator. So you'll get Laplace operator times this unknown coefficient function equals delta function. You invert Laplace operator and you will get the Gluon-Green function. So in the first order, it's rather trivial. But I want to present more general method which would explain to you how you get higher orders. And not only that, I want to explain to you how you get gauge invariant iteration. You want to get gauge invariant version of the perturbation theory where you don't separate, you see, this separation means you start with specific gauge, and then you have Gluon propagator. That's not unique. There could be gauge term in the Gluon propagator. So I want to explain to you how you do iterations where you don't really break gauge invariance. So at this point, we could actually fork. That's the idea. You could either describe the planarity combinatorics, how we get planar graphs, or we could fork and describe the problem of regularization, or we could jump to the momentum loops where all these problems disappear. So do you want to be overloaded with problems which bother people for 40 years before they disappear or not? I think you do, because you're still, I'm sure you still think the problems exist. So I have to show these problems before I show how they disappear.
Do we have to choose? Or do we,
Well,
can we just do all three?
Huh?
Can we do all three?
Well,
A,
let's
B,
do all
C.
three. That's right. That's my spirit. Of two
Easy solution.
bad alternatives, choose both and fight through. Okay. So how the loop equation generates planar graph? I have to do two things. First of all, I have to do something with delta function, right? Because we don't like infinities. And the beautiful way of getting final graphs is dimensional regularization. In our case, dimensional regularization doesn't work. We don't want to change geometry, but we don't mind replacing delta function by some singular representation, namely, if it is, say, you could replace delta function by some small power of the covariant operator, and that in the limit when power goes to 0 would represent delta function. So there is a zeta regularization of the covariant operator of the delta function using fractional power of covariant operator, which is a very natural thing to do. It's called zeta regularization. So let's suppose we do that. So let me explain how we do that, because here I will just quote pages from my old report, because I was too lazy to reproduce all these graphs again. When I was younger and lived in a country where suffering purified, I didn't mind drawing that for many, many hours, but now I can't. So
Now that you live in America.
so instead I use technology to do that. So here's from my 83 report. So regularization by means of epsilon zeta regularization of the loop equation. You replace delta function by the power of gradient, and then that effectively introduces, it splits the point. It splits these 2 points here, right? And let me show you on this plot what it does. If you introduce this covariant, if the regularization, what you do is you introduce these little wires connecting these 2 points. So instead of having delta function, you will have some kernels integrating these 2 closed loops. So there will be loop CXY and CYX. They will be connected with little wires. And they will have sum over all the positions of these wires. There will be integral d, call it gamma 1, d gamma 2 with some weight, which reduces to delta function. And then you will have W of CYX times gamma 1 times W of CXY times gamma 2. We'll have two wires connecting these two, making these two loops close, otherwise it will be not gauge invariant. And there will be some kernel here, which would be designed so that the loops will become very short, and you will in the end get the same delta function. Once you do that, you could iterate equation safely. You are not afraid of any infinities. And then you will get what I call last graph. So let me explain you what you get. So I introduced these little wires closing the loops. Now I could separate the points. And you will get, instead of this integral, you will get some kernel. I'm explaining that here. You'll get some kernel. You will get that weight with small power of epsilon. You should get integrated over proper time with this factor epsilon, and that would lead to divergent integral small proper times. When proper time is small, that forces this path to be very short. So what you get is this equation, which looks the same as the original one, but now these loops are finite. But they are not now random. They are now integrated over with some weights. So that's a regularized version of the loop equation, which is a gauge invariant equation, which can be iterated, which has no infinities. But in the end, it will have poles in terms of this epsilon, which goes to 0. And when you do these poles, you use this Hopf version of dimensional regularization, and you'll find some expressions, which, by the way, are not yet finite, because you want also to integrate over these paths and get that into the meson propagators. That's when the epsilon poles will cancel, not before. So once you do that, you will get this integral. So instead of delta function, you will get this integral involving k to the epsilon in denominator. That's regularization. Then when you do inverse operator, what you get is this. So once you, in the first order, you will get just one gluon propagator. See here you get gamma of epsilon plus 1, which is now safe, and you will get 1 over k squared. Anyway, you will get this diagram. And the next order, you will simply have to iterate, substituting for each of these two windows the previous expression. And when you do that, you will get exactly 3 diagrams. You will get, so here is the left, W, which you represented as the first diagram. But then there is another one. See, there is this term when this point lands just on this path here. You don't have to ignore it. And then there is this term. So once you do all that, you will get second order. So you will get diagrams like that, you will get diagram like that, and you will get diagram like that. So what is interesting is that in this order, you don't yet see the ghost loops. In next order, you will see them. Again, the ghost loops come because when you integrate over closed loops, you have to make all these integration points go all the way around each loop, and that would include them going into these little wires. And that's this contribution of this loops integration point going into wires actually brings the higher order diagrams. But basically, when you consider the whole equation in the highest orders, what will happen is that when you apply L operator to this W, you have planar graphs on the left and planar graphs on the right. And this line, in fact, is the line of this operator. What does it do? This loop operator catches one gluon emitted from the quark line. It kills all the gluons lines crossing that one. And then it also uses the terms when there is a double operator, because in the quark loop, there is not only the single gluon emission, but also double gluon emission, because there is F mu term. Therefore, there are gluon graphs like that. There are gluon graphs not only like that, but also like that. So when you apply L operator to the sum of gluon graphs, it does all these cancellations. So when you originally you had all kinds of gluon graphs. These are amplitudes. So they were all kinds of gluon. They were planar, but in general they didn't have that factorized structure. Now, when you differentiate, what happens? It picks only one line, which goes through all the way, and then there is factorization of these W's. But the lines which were like that are all canceled. That's how operator L acts. So there will be no lines like that. So, but there will be lines like that. There will be lines like that. So all these kinematics was very carefully analyzed by us with McCain.
And that dotted line is the wire?
Yes.
Yeah.
Well, no. In this case, dotted wire line is already, yes, it is the wire. When you apply the operator L, it actually makes operator gluon propagator delta function.
Yeah.
And that has to be replaced by wire, double wire. And then you have to really carefully keep all the terms, keeping the wire finite. And in the end, after you recover the graphs, you could make wire small. Actually, you should never do it because you will get infinities. You have to compute physical quark amplitudes like I described. Only then you could send epsilon to 0.
I have a quick question. The sort of loop that was fully contained in the wire.
I think.
No, that's.
Oh, no, it's okay.
Yeah. So for the loop that was fully contained within the wire.
What was contained?
So it was the third graph.
Yes.
There was the sort of vertical wire with a quark loop starting and ending, or sorry, gluon loop starting and ending
Which
on the
one?
wire.
I'm showing it there.
The third diagram in the middle row.
In the middle row, the third one.
Yes.
The last one.
Yeah.
Yes.
For that one, I see you in the sort of bottom.
No. After you do inversion operator, these propagators are no longer short wires. That's the whole thing.
Yes.
Inversion operator makes them long wires. So if you don't carry that when they're short, you will not get results when they're long.
I see.
So that only proves that really this equation makes sense only if you introduce wires. Otherwise, really don't understand what you're doing. If you introduce wires, you have very reasonable planar graphs, not calculable, of course, but still they have no miracles. It's just iterations and inversion of operator, which translates, it is basically multiplying by 1 over k squared, so it makes a long propagator instead of delta function. So, okay, let us do it more algebraic way. You could say the following. I call the bootstrap equation. Area derivative will have two terms. in general. One term will, which I call B alpha, will have involved derivatives times some vector, one, it will correspond to one gluon vertex. And there will be term with two gluon vertex. But area derivative corresponds to F mu, and F mu have two terms. One is d mu a nu minus d mu a nu, which is linear, the first term, and another is commutative. So there are two terms. And this one is, in perturbation theory, is smaller than the first one because gauge field is proportional to up and down. So it's expansion in nonlinearity. So the thing is that in order to get the perturbation theory, you have to do very, very simple thing. You have to rewrite this equation as follows. It is this operator inverse times this, and G nu is the right side. Now, the thing is you want to expand in terms of the of this commutator, because commutator has higher order in coupling constant, because each commutator brings F mu, which is, commutator means, yes, commutator is higher order because it brings F mu. So when you do that, you will get expansion of this operator. You will get expansion in inverse powers, geometric series, basically, and that these terms will generate higher and higher order graphs. But these expressions now can be written in a gauge invariant form because you could now, when you have this inverse operator, you could write it as a path integral. It's the same thing. Inverse operator, again, could be exponentiated, and when you exponentiate it, you could apply the same trick, so you'll get path integral. And when you get path integral, you get what I call bootstrap equation. So you take this delta, so this line is a delta function, this is your short line. Now you have this sum over paths, which are now basically replacing the short line. Basically, delta function means this point equals to that one. So then, but you have this W, which are doubly depending on the path. So we have integral equation which involves sum over paths of these two W's. So I never break the closed path. I have this integral equation with W and W, gauge invariant is true. And then when I expand, substitute for each of W's the previous orders, I will get some of these planar graphs. And that is the gauge invariant way to derive perturbation theory. It turns out equivalent to the Faddeev-Popov graphs. Okay.
But the Faddeev-Popov graphs are, but you don't recognize the individual graphs, do you?
Their initial graphs correspond to different part of integration in my glass graphs.
But then in what gauge?
In Landau gauge.
I see.
In Landau gauge, it's easiest. Yeah, you would actually introduce in the zeroth order. You could introduce gauge because in the zeroth order you could. It's ambiguous because it's double integral over the loop. So the first order is ambiguous.
I see. So the gauge choice is already there in how you represent the propagator, which with the gauge dependent part canceling when you integrate it.
Yeah, because it's integral of closed loop, you could add derivative terms.
Okay, I got it. Okay, great.
Yeah, but the easiest one not to add them then it is Landau. Not Landau, it is Feynman gauge, whatever. But anyway, that is a very well-defined, well-studied thing, which is kind of not questionable. What is questionable is how to go beyond perturbation theory. But I want you to understand that it is not something symbolic which needs to be redefined, and it is something very well defined. It's just not easy to work with, but it's something which can be regularized in a gauge invariant way, and then it is a very well-defined theory. Ambiguous, of course, because there is more than one way to introduce these wires with certain weights, and that's okay. We want to find something which would, in the limit, become local theory.
Can I ask something? Are Can we derive the MM equations directly on the lattice?
Oh, yes, of course, that's how it works.
Right, and then there's no, then the regularization issue is just.
Oh, the
absent
lattice
what
is
the-
rather trivial, yes. But on the other hand, on
So
the
what,
lattice,
but
you
then
don't see,
what plays the role of the wire on the lattice?
no, there is no wire.
There's no, so everything is just, everything.
Yeah, on the lattice, you don't need to do anything, you just,
It's just anchored on the same point.
that's right, every link on the lattice corresponds to unitary,
Right.
this elementary unitary operator.
Yes.
And then you have, you see, you integrate over group elements U, and there is similar formula for this.
And L is a discrete triple derivative somehow?
Oh,
What
L is
Yeah.
something crazy,
Yeah.
and ugly, but it exists. L is the following thing.
Just taking the respect.
You take
Huh?
your lattice loop, I don't know how to draw it,
Yeah.
whatever. Take the lattice loop, right? So what
And
you
so, and
do,
so just to make sure, the right-hand side of the equation is now literally the plaquette going this way times the plaquette going the other way?
oh yeah, right side is basically the same thing, you contract
Yeah.
2 points.
But now there's literally at the same point, because that's okay on the lattice, right?
So what you do is do the following, you have this, your thing, you take one plaquette. So suppose there is this one plaquette, okay? This one plaquette, okay? Then you take a plaquette or part of the loop, then you move it. Take the plaquette, then you
No,
subtract
yeah.
the opposite orientation of the plaquette minus the plaquette going other way.
Yeah, I mean, it's the,
Yeah, take the plaquette, rotate it, subtract, and then shift the whole thing.
Right.
So there is indeed a very ugly, but well-defined discrete operator.
why is it, I mean, why is it any uglier or less ugly than the one that you've written down?
Because this one has symmetries, for example, Hodge duality, and this one doesn't have anything of that. There are all the symmetries of the gauge theory, including instantons and rotation and chirality. They're absent on the lattice. So lattice comes with a big sacrifice.
Yes, I agree.
Yeah, but of course it exists. But the thing is, we know what is wrong with the lattice. If you literally take the lattice and don't care about what are you doing, you will get a wrong face. There is this roughening face transition. So lattice is a very, very tricky thing. It's very easy to get. For example, there is a Iguchi-Kawai model which solves the lattice loop equations, but it is not QCD.
Sure.
That's why it is very important to do something with momentum loop equation, because they are not only finite, they are Lorentz invariant, whatever, and finite. So the whole point of lattice was to have something finite. It's because it was not known that there is momentum loop. Okay, I'm almost done. I'm almost done. Thank you for your patience. So now the complications. People found out that when the loop is smooth, but there is a cusp, 2 cusps.
Yeah.
At every cusp, there are logarithmic divergences. That's, in my view, was a trap made by gauge theory god to trap smart kids and then burn them.
Gauge theory.
And one of these smart kids was Grisha Karchensky, whom I quite respect. So indeed, if you have the loop with, say, 1 cusp, then in the vicinity of this cusp, there are all kinds of gluon graphs, and they have singularities. You could sum up these singular terms, and you will get something exponential of something like theta, a tangent theta minus 1 or something like that, times logarithm of whatever cutoff you have. You get some logarithmic divergent things. Then smart kids say, we can normalize it because that's local. Indeed, there is two cusps. For each cusp, you could get the factor which normalizes it, and then what do you do if there are different number of cusps on the left and the right side? Like that becomes very messy, and it means that indeed you really don't need to normalize Wilson loop. Here is an example. That's what you see in the loop equation. You have two loops. One loop so on the left side, you have the one loop of the figure 8 shape, right? And that loop has 4 cusps, right? There are 4 wedges. There could be gluon diagrams going between each pair of lines. So there will be singularity related to theta 1, singularity related to theta 2, theta 3, and theta 4. So it'll be like 4 factors. But on the right side of the equation, there is only this W times this W. There is no W for this part or this part. So there will be 4 normalization factors on the left and 2 normalization factors on the right. How could they match? Well, they cannot match because you say, okay, there is a coupling constant in front, but coupling constant couldn't depend on these angles. Coupling constant is universal. So you cannot really normalize the Wilson loop MM equation because the left side and right side have different counting of cusps.
Sorry, why do you not have, this is probably also stupid. This is probably not stupid, but why can you not have like gluons going from 2 edges that are not adjacent to each other? Like if this is a picture.
Because it's factorization. On the right side, we don't have. You see, on the left side, indeed, we have these gluon graphs. On the left side, we have the full 8-shaped graph.
I see. Okay. I see.
And diagrams for that full-shaped
Have everything. I see.
have 4 sources of divergences for each wedge in this picture.
Okay. I see.
So that's a problem. That's a real problem. So on the left, you see, on the left we have 4 angles, and therefore we have all 4 normalization factors. So on the left you have Z1, Z2, Z3, Z4, and on the right you have only Z1 times Z3. And you cannot reabsorb missing factors into coupling constant because the coupling constant shouldn't be dependent on the angles. So what did we learn? That this delta function localizes the contour integral at the intersection. It does not change the local wedge geometry, so there is no freedom to supply extra angle dependent contour terms. So you might want to say, okay, that's the source when you need to mix. There is a different, Wilson loop operator with different kind of number of wedges are not multiplicatively normalizable. There are mixed with others. So you could find what I call excuses, but that's not a solution because remember, we don't really need to make it finite because if it is finite, then we have another problem. If it will be finite, then what about quark amplitudes which are integrated of that? If it's finite, then that will not be finite. So it should be infinite just enough to, together with infinities coming from the path integral of W in physical observables, altogether observables must be finite. So what really the normalization group tells us? It tells us that there are some local operators. Remember, a normalization group was designed to deal with local operators, which have indeed some matrix or anomalous dimensions or matrix of anomalous dimensions. So in the heart of this normalization group for the gauge theory, there is a notion of local operators. And local operators indeed could multiply normalizably with matrix normalization constant. And there should be some matrix version of the beta function equation, but not in case there are indefinite number of wedges and cusps on the loop. It is, especially if they are infinitely dense. So it absolutely doesn't apply to non-local operators like Wilson loop. So I'm finishing my lecture. Here are the lessons. So this loop equation provides defining planar loop dynamics. It's not just some identity in the corner of the theory. It is a replacement of the dynamics. It's honest replacement of the gauge invariant dynamics. If you add to the Wilson loop equation condition that at infinite loop it goes to 0, and at infinitesimal small loop it goes to 1, then you should iterate this equation in coupling constant, and you uniquely reproduce the perturbation theory. That's one observation. And now another observation is that observable amplitude are singular path integrals over Brownian loops involving W and Digger amplitudes. So the fixed loop WFC could have cusp or perimeter singularities, but in the physical Brownian path integral, these are not a normalization problem that controls observable operator. That's, by the way, this safe formulation was suggested to me by AI. What I said that it's that the normalizability of what I said in my version was that normalizability of Wilson loop goes away and good riddance. So that's what I really think. Now the way forward is to regularize my equation by geometry and try to go to momentum space where the infinities are absent, and then to local limit and see what happens. So you don't really want to go to local limit until you go to something which is supposed to be finite, and momentum amplitudes are much better. They could also be infinite, but they are not. If you look at the equation, you find out that the fixed external momentum loop, Wilson loop, is just finite. And that's what we're going to describe on the next lecture. Any questions, guys? I'm sorry, I really bored you to death with all these details, but I learned that this is a place where people love details.
So, I'm confused by something. Can we go back to the, just to the four cusp picture?
Which one?
Just your,
The eight,
just the, yeah, this one. So, if everything is regularized, right?
No,
No,
in my theory, yes, but
yeah, but let's say we do, but it's fine. So you regularize something. You say that the regularized objects manifestly satisfy the MM equations, right?
yes.
But then on the left-hand side, even after regularization, of course, it's finite, but you're going to get sort of 4 logs, right? You're going to get a log from every, I mean, if you actually if you do all the integrals, you're going to get 4 logs on the left-hand side. On the right-hand side, you get 2 logs. How is this consistent? I mean, in other words, it has nothing to do with the infinities. It's just
my answer is you don't really get logs because you cannot remove regularization at the level of equation. You have to solve it first and then remove regularization. Equation doesn't have finite limit when you,
I'm not trying to remove the regulator. I want to keep the regulator fixed.
But then you don't have logs.
Fixed. Huh?
Then you don't have logs.
Sure,
you have more
yeah.
complex things.
Well, you have some kind of log of your, I mean, you have some log of U squared over P squared, you know, surely, I mean, there's a log, it's finite, but that looks like a log. It's something that as you make the mu, epsilon smaller and smaller.
Okay. I have to take that challenge. So consider the H-shaped path
Yes,
and consider regularized equation.
yes. How is it consistent? Yes. Because it is consistent, you tell us, but then from the picture, it seems like one has 4 logs, the other has 2.
It is true, but I don't think that if you really keep regularized equation, then you will get just these 4 logs. You will get more. If you have these little wires, you will get more than that, I think. You will get some extra infinities coming from this integration over these wires. So you have to be careful here. It's not finite, right?
So maybe it's because there's some other, so maybe there's some additional logs. I mean, I presume everything is logs, but there's some additional logs from also the kind of the direction in which these are pulled apart.
There might be
That's
additional logs
Right.
coming from integration over these wires.
I think it would be very instructive to see how they
Yes,
all
that would be
get
indeed
worked
very
out.
instructive.
Yeah. 'Cause
And
that-
also, don't
that-
forget
right.
that operator L, when applied to the loop, could introduce infinities or cancel infinities of its own, right?
Sure, right.
So basically, it could happen that when you do the regularized expression and
Right.
apply operator L to this picture,
That must be what's happening. It must be the L is canceling two of the logs
L
somehow,
may
right?
be canceling
That,
these
right.
guys.
Yeah, I'm guessing that the L is canceling the ones on the,
Outside.
on the outside, yeah.
Yes,
The L
That
may
must
canceling
be.
the ones on the outside, right.
yeah,
Right.
that must be.
But that is, I guess what you'd say the sort of party line would be is that you're somehow renormalizing the loop equation somehow, right?
Yes.
That's not.
You see, L,
right.
you see, it's controversial. If you think of L as a local operator, it
Yes.
could not bring something depending on these angles, because that is a global, that's not something. Operator L involves infinitesimal operators at the intersection point. So I don't see how that could depend on angles. Unless you regularize. If you regularize, then indeed, this dependence could appear. But locally, if you think of local operator, you said, okay, on the left, you make infinitesimal changes which don't feel these angles, right? So, but that's a good exercise, I would say. Try to see actually what happens with these diagrams which go between these two lines. They must somehow, well, we know that operator L leads to factorization. So operator L must.
It must be canceling those things.
Yeah, it
somehow
must be canceling.
canceling them. So maybe that's the point. It's not that it depends on theta, but it just cancels the difference between two terms, right? Maybe it's like on one side, it's
Yeah, I would say that paradox may be not such a obvious paradox as I presented it, because if operator L simply cancels all the gluon graphs.
It
between the-
separates
Exactly,
it, right?
yes,
If it
exactly.
separates
Separates
it,
it. So
then
it
it doesn't
separates
see
it.
the,
These are connecting the two
yeah,
loops.
the things that
Right.
are separate.
right.
Yes, that is, I think,
Okay, you're
true.
separating.
But that
That's right,
still
yeah, right.
means that renormalization is not useful here.
Well, I would say it's not needed. Then I would say that the operator is.
Yeah,
well
another point of
defined.
view still valid, that we don't need to regularize something which is in the middle of the path integral, and we'll get another infinities, and also paths are not smooth. So that argument remains. This 4 thetas is maybe exaggerated problem, because then probably it is explained by.
But the same thing that makes it factorized to begin with.
Yeah,
right.
yeah. Admitted.
I have another, I mean, this is jumping ahead a little bit, but it's a vague question, so you can ignore it if it's not a useful question. But something which is sort of bothering me a little bit is that ultimately you want to think about these Wilson loops sort of physically as the boundary of some string world sheet or something like that, right?
Make my idea, that's
yeah.
what I am going to
Right.
talk about.
But then what's bothering me is that in exact string theory, in string theory, it makes sense to talk about infinitely thin strings. That's the whole point, right? They don't have any structure. For QCD, we expect these QCD strings have some thickness, right? They have
Not
size of order.
in large and limit, maybe at infinite and it is not. Well, I'm going to present something which looks like infinitely thin string at large and.
Okay,
But not,
okay,
string. Not string is string.
Okay, that's kind of the
holographic
answer to my
string.
question, but that's the answer. Well, anyway, but that's because I would think that any equation that we write down, any equation that would involve something like a sort of physical QCD string with some thickness, I would think, maybe you're saying that we should not think of this something with thickness, but I'm just saying what the sort of standard picture would be. It seems sort of funny to talk about infinitesimal motions of the string where the whole picture only makes sense on scales that are spread out.
No. I
over
think
the,
that
QCD
the
scale.
clean problem
Right.
is infinite and large and QCD, planar
Yes.
QCD. And in that case, I hope, and I will go and present to you, infinitely thin string which satisfies everything without excuses.
Okay.
So would there be some kind of way of bringing n down So, like expanding around large N that you see it
Oh,
develop in
yeah.
size.
There is one over an expansion, the same solution which I will derive for infinite N would contribute to the planar graph with higher topology.
Mhm.
That string picture remains. Once you get the leading order, that same string would get involved because there are loop equations relating
But
next order to previous.
I think, but let me just say again, this is some novelty of your picture. I think most people would think, even at infinite N, that the QCD string is thick, has a thickness of order, there's a scale, lambda QCD, it has a thickness of order lambda QCD. And even if we take an
That
infinitely long
means
string.
the large N
yeah,
theory is
yeah.
unsolvable, right?
Well, or it's very unusual, yeah, I mean, but it could still be weakly interacting, but it's not a conventional, it's not
Look,
just an Navier-Goto string, right? I think you're saying it's infinitely thin and not Navier-Goto. That's what
Right.
you're saying. You're saying that it's a string but with no vibrations on it.
That's
Yeah,
right,
It's not,
it's
doesn't
a
have any.
holographic
yeah.
string.
Okay, but, fine, but I mean, physically, if I take a quark, if I hand you a massive quark, an infinitely heavy quark, me an infinitely heavy quark, I pull them apart from each other.
Oh, there's a
rope,
force,
There's a
but
force.
that force
Yeah.
is not wiggling.
Exactly, you're saying it doesn't wiggle. You say if I go like this, ding, 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 there's
It
no
is a
waves
stick.
that
It
go
is a
down.
stick.
It's a stick. That's what you say.
Well, it's
That's
not
what-
a stick, it's something curved.
No, I know,
It's
but,
a
but,
cavity.
but it doesn't have, waves on it. It doesn't have waves on it, right? And we'll talk about this later. I mean, there's lots of reasons to think that it should have waves on it, right? In a relativistic theory, you should not have exactly rigid objects. If I wave it here, it should take time for it to propagate. If I wave it here locally, that's why we think there's waves that propagate from one end to the other. In any case, we're gonna come back to
Well,
that.
you
but I
have
think
in
that's,
mind
yeah.
the picture of the gluon flux connecting quarks.
Yes, exactly.
I'm saying
Yes.
that fluctuation of that flux
Yes,
is not necessarily describing a fluctuation of the shape of the flux. It could be the same rigid shape, but gluons inside are fluctuating. The field, you see, fluctuation is not necessarily means this spine is vibrating.
okay. But anyway, we're gonna get there, but I just wanted to say that that's part of this logic, because, if I wanted to give a reason, 2 hours ago, why, at least a reason why you might be skeptical that solving loop equations could solve the theory. The first thing I would say is that the equations are super local, and yet the string is thick, right? So it seems unlikely that an
And
equation.
who said this thing is thick?
That's exactly it. So but it seems like this is the fundamental point somehow, is that for you, the string is gonna be.
I
infinitely thick.
don't
That's
have
right.
this humanity, I
Yes,
have to
yes.
solve equation.
No, I got it. No, but the thing is that, anyway, yes, yeah.